Pluto, once recognized as a distinctive and valid planet in our solar system, was for many years considered a special entity. However, in recent times, discussions led by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku have placed Pluto back under scrutiny, sparking renewed interest in its status. These experts have proposed that Pluto may be on a possible collision course with Neptune, a theory that has stirred up many questions. How could such a massive impact take place? What would the consequences be for both planets and for the solar system? Are we witnessing a strange cosmic phenomenon? Or is there a more intricate and profound explanation behind this idea? Let us explore what such a potential Pluto-Neptune collision could mean for us. Once seen as a smaller, more distant object in the solar system, Pluto continues to generate a great deal of interest among scientists. According to significant studies from leading professionals, Pluto's orbit is dangerously close to Neptune's, and this has led some astrophysicists, including Tyson and Kaku, to raise alarms about the possibility of a catastrophic crash between the two bodies. The looming question now is, could such an event present a real risk to Earth? How could it even happen? Pluto's orbit is one of the most unique in our solar system. It takes an extraordinary 248 years to complete a single orbit around the Sun, which means that since its discovery in 1930, Pluto has yet to finish one full cycle. However, that's not the only peculiar feature of Pluto's orbit. It is elongated in shape, unlike the more circular orbits of the larger planets. Furthermore, Pluto's orbit is tilted at a 17-degree angle compared to the plane of the solar system, making it one of the most tilted orbits observed in space. This extreme tilt, paired with its irregular shape, adds complexity to its journey through space. One particularly intriguing aspect of Pluto's orbit is its interaction with Neptune's orbit. For about 2 decades during each orbit, Pluto actually comes closer to the Sun than Neptune does, defying expectations about the relative positions of these planets. This brings up a crucial question. Why hasn't Pluto and Neptune collided? The answer is found in the gravitational forces at work within the solar system. Pluto's orbit was a mystery to astronomers immediately after its discovery. Unlike the other planets, whose paths remain nearly flat and aligned along the solar system's plane, Pluto's orbit was tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's doesn't automatically mean a collision, thanks to a gravitational interplay that stabilizes both orbits. This balance, known as the three-body problem, refers to the way 3 celestial bodies, Pluto, Neptune, and the Sun, interact through their gravitational pulls. Essentially, it's like trying to predict the future paths of these bodies by accounting for their current positions and the gravitational forces they exert on one another. In Pluto's case, this phenomenon reveals how its orbit, Neptune's orbit, and the Sun's gravity all work in a balanced way to prevent a collision. Astrophysicists have pointed out that the stability of the Pluto-Neptune orbit interaction is helped by a mechanism called libration. In this context, when Pluto crosses Neptune's orbit, it does so at a distance of at least 90 degrees away from Neptune, meaning that the two bodies will never be in the same place at the same time. There's also the phenomenon of degree libration, which refers to the oscillation or shifting of Pluto's orbit around its path. This means that Pluto doesn't cross directly into Neptune's orbital plane, further minimizing the risk of a collision. Another important factor contributing to Pluto's orbital stability is the gravitational wobble phenomenon, known as VZK wobbling, named after the scientists who analyzed how celestial bodies move in space. This effect explains how Pluto, Neptune, and the Sun influence one another's motions through gravity, helping keep Pluto's orbit stable. Despite Pluto's seemingly erratic movement, the combined forces at work ensure that its path remains relatively consistent over long stretches of time. The three-body problem and the forces governing these celestial motions are crucial for understanding how planetary orbits evolve over time. These interactions between Pluto, Neptune, and other bodies allow us to learn more about not only Pluto but the broader workings of our solar system. Numerical simulations conducted in the late 1980s revealed that although these stabilizing forces help maintain Pluto's orbit, slight variations in its initial conditions could cause its orbit to become more erratic over extended periods. However, despite these potential irregularities, Pluto's orbit remains relatively consistent over the millennia. Recent computational models have further illuminated the ways in which Jupiter, Saturn, and Neptune stabilize Pluto's path. For instance, Neptune and Pluto are in a resonant orbit, meaning that for every 2 times Pluto orbits the Sun, Neptune completes 3 orbits. This resonance is crucial for maintaining the stability of Pluto's orbit. However, Neptune is not the only planet that influences Pluto's path. Jupiter's gravitational pull also plays a significant role. Even Saturn has been shown to contribute to the stability of Pluto's orbit. These simulations suggest that the gravity of Jupiter alone is powerful enough to maintain Pluto's trajectory for billions of years, if not indefinitely. The cooperation between Neptune, Jupiter, and Saturn is therefore crucial in ensuring that Pluto remains on its stable orbital course. Without these stabilizing forces, our solar system would be far more chaotic, with objects like Pluto potentially colliding with other bodies or being flung from their orbits entirely. The study of such interactions not only helps us understand Pluto's orbital mechanics, but also provides valuable insights into the broader functioning of the universe. In light of this, understanding Pluto's orbit becomes even more important when considering theories about a potential collision with Neptune. The study of Pluto's complex orbit demonstrates the dynamic nature of the solar system and how the forces acting on one celestial body can influence the entire system. It's also a reminder that even orbits that appear chaotic can still achieve a state of balance through these intricate interactions. The concept of orbital resonance is key to understanding the delicate balance that exists within Pluto's orbit. This principle explains how Pluto's position and velocity, even in an irregular path, can still maintain a stable orbit over time. Programs that simulate these orbital mechanics have provided essential insights into how Pluto's orbit interacts with those of other celestial bodies, including Neptune. Small adjustments in the parameters of these models can show how tiny changes in Pluto's position or velocity can significantly alter its orbit over time. Despite the stabilizing forces that maintain Pluto's orbit, such as asymmetric libration and degree libration, its path can still be highly unpredictable. Even slight changes in Pluto's initial conditions or velocity can lead to large shifts in its long-term trajectory. However, despite this seeming unpredictability, Pluto's orbit remains remarkably stable over billions of years, indicating that there is an underlying order to its movement around the Sun, even if it appears chaotic at times. This unpredictability presents significant challenges for astronomers, who must account for the complex, evolving nature of large planetary orbits like Pluto's. While numerical simulations are an invaluable tool for predicting the future behavior of celestial bodies, they also demonstrate the limitations of our predictive models. These simulations depend heavily on the accuracy of their initial conditions, and even the smallest error in those conditions can drastically alter the results, making it difficult to make precise predictions. The complex nature of Pluto's orbit serves as a constant reminder of the ever-changing, dynamic nature of the universe. While astronomers have made remarkable progress in understanding space, Pluto's unpredictable path illustrates how much more there is still to learn. Studying the gravitational effects of the giant planets like Jupiter, Saturn, and Neptune on Pluto helps astronomers gain valuable insights into the broader dynamics of our solar system. It shows how the positions and movements of individual planets can have far-reaching consequences for the stability of other objects in the system. Despite these complex and stabilizing factors, leading astrophysicists have recently raised concerns about a potential collision between Pluto and Neptune. Neil deGrasse Tyson, a prominent astrophysicist, offers a fascinating perspective on the mysteries of our solar system, using Pluto as a case study. Tyson, who played a key role in reclassifying Pluto from a planet to a dwarf planet, emphasizes the importance of continuously evolving our understanding of celestial mechanics. He believes the reclassification of Pluto was not a loss, but rather a necessary adjustment as our knowledge of the solar system deepens. Tyson views Pluto's unusual orbit and its interactions with Neptune as a testament to the unpredictability of space. While he acknowledges that Pluto's orbit is stable for the time being, he warns that it could change significantly in the future. This possibility highlights how much we still have to learn about the forces that shape the solar system and the far-reaching implications of those forces. Tyson's perspective emphasizes the unpredictable and ever-changing nature of space, reminding us of the complexities in celestial mechanics. His analysis of Pluto's orbit, especially in relation to Neptune, underscores how even long-studied planetary movements can still hold surprises. Despite the apparent stability of Pluto's current orbit, he suggests that this situation could evolve over time due to the dynamic forces at work within the solar system. Tyson argues that our understanding of these forces and their impact on celestial bodies is far from complete, which makes the study of Pluto and similar objects even more intriguing. The reclassification of Pluto as a dwarf planet, a move that was met with controversy by some in the public, actually aligns with our evolving understanding of the solar system. Tyson explains that this adjustment was a necessary step in refining our classification system for celestial bodies. As our tools for exploring the universe improve and our knowledge deepens, it becomes clear that Pluto, while no longer officially considered a full-fledged planet, remains an important subject for scientific research. This evolving understanding is not limited to Pluto's classification. It extends to broader questions about the stability of our solar system and the forces that govern the motions of planets, moons, and other objects. The work of scientists like Tyson and Kaku continues to shed light on the complexities of celestial mechanics and their implications for the future of our solar system. These discussions, although rooted in the specific case of Pluto, have broader relevance for understanding how the universe works. Kaku, another key figure in the discussion about Pluto and Neptune, offers additional insight into the potential risks and dynamics at play. His perspective builds upon the work of Tyson and others, exploring how even small changes in Pluto's orbit could potentially lead to a collision with Neptune or affect the stability of other celestial bodies. Kaku's work helps illuminate how we might be able to predict and possibly mitigate such risks, even as we continue to expand our understanding of the solar system's most distant objects. As scientists work to better understand the possibility of a future collision between Pluto and Neptune, they rely on sophisticated simulations and models to predict how the gravitational forces acting on these two bodies will evolve over time. These simulations help scientists track the movement of Pluto and Neptune, taking into account the complex interactions between their orbits and the influence of other planets like Jupiter and Saturn. Such research is critical not only for understanding Pluto's future, but also for improving our ability to predict the behavior of other objects in the solar system. Despite the relatively stable relationship between Pluto and Neptune in the present day, there is still much uncertainty surrounding the future of their orbits. The intricate gravitational dance that keeps Pluto and Neptune on their current paths could, over vast periods of time, shift. Even the smallest variation in the initial conditions of their orbits could cause their paths to diverge, leading to potential collisions or other disruptive events. This unpredictability highlights the limitations of our current knowledge and the challenges that lie ahead in studying the long-term dynamics of the solar system. Understanding the forces that influence Pluto's orbit is just one piece of the puzzle. It also provides valuable insights into the broader dynamics of our solar system. The relationship between Pluto and Neptune is an example of the delicate balance required to maintain the stability of planetary orbits, not just for these two bodies but for the entire solar system. In this sense, the study of Pluto's orbit is essential for gaining a deeper understanding of how celestial bodies interact with one another and how the solar system as a whole remains in balance. As we continue to explore space, the study of Pluto and other distant objects becomes increasingly important. These objects, though far from the Earth, hold clues that could help us understand the origins and future of our solar system. By examining Pluto's unusual orbit and its potential interactions with Neptune, scientists are learning more about the forces that shape our cosmic neighborhood. These insights may have implications not only for our understanding of Pluto but also for the study of other distant objects, including exoplanets and stars in far-off galaxies. The ongoing research into Pluto and Neptune also serves as a reminder of the need for continuous learning in the field of astrophysics. Just as Tyson and Kaku have adapted their views in light of new discoveries, future generations of scientists will need to remain flexible and open to new ideas. The universe is constantly changing, and our understanding of it must evolve as well. As technology advances and our exploration of space deepens, we will likely uncover even more surprises about the nature of planetary orbits and the forces that govern them. In conclusion, the potential for a collision between Pluto and Neptune is a fascinating and complex topic that continues to captivate scientists and the public alike. The unique orbital characteristics of Pluto, combined with the intricate gravitational interactions at play, make this a subject of great interest. While the current stability of Pluto's orbit is reassuring, the possibility of future changes serves as a reminder of the unpredictable nature of space. As we continue to study Pluto, Neptune, and the other objects in our solar system, we gain deeper insights into the mechanics of our cosmic neighborhood. These insights not only enhance our understanding of the past and present, but also shape our predictions for the future, helping us better comprehend the vast and dynamic universe we inhabit.